Hello guys, we will be discussing or actually solving together a new problem. This is problem 753 in your book, the paper book, the 14th edition. It's in page 367. This is a very simple problem as well. It's asking us to find or to draw the shear and bending moment diagrams. Now, as you can see here, we have distributed loading having a geometry of a triangle. And now we have two supports. We have roller at A and roller at B. As we said, the first thing that we need to do is to find the support reactions. So in order to do that, we need to convert this distributed loading into concentrated load and find its position. So this is something that we've done so far several times. Easy. Now we said that the concentrated load of this distributed loading is basically the area under this curve. So it's basically the area of the triangle. So we say that the resultant force of this triangular shape is half multiplied by the base multiplied by the height, and this gives us 2.25 kilonewtons. Right? Now it's kilonewtons, not kilonewtons per meters, because it's not concentrated load. The position, as we've discussed several times, it could be 2 over 3, or it should be 2 over 3 from the acute angle, or 1 over 3 of this distance from the right angle. So now it's, for example, if we go from left, so it's 2 over 3 multiplied by 3, and this is 2 meters. Now, so basically we've converted this whole load into a single point load at a distance of 2 meters. Now we can find our support reactions. Now, as we said, since we have only reactions in the y direction, then we don't have, for B, we don't have Bx. Bx is definitely 0 because we don't have any forces in the x direction. So we have By and we have Ay. We take moment around any point, for example, take it about around or about P. So clockwise is positive, summation of moments around point B is 0. So we get minus Ay multiplied by the distance. This whole distance is 3 meters. Be careful, don't mix. So minus Ay multiplied by 3 because it's going clockwise, plus 2.25, which is the value of this concentrated load. It's going counterclockwise, so it's positive, multiplied by this distance. This is 1. So if this is 2, then definitely this is 1. This is 0. So we get Ay equals to 0.75 kilonewtons. Now, if you do the summation of forces in the y-axis is 0, you'll get By. Please solve it yourselves. You'll get a value of By of 1.5 kilonewtons. Simply, if you sum these two forces up, 1.5 and 0.75, this should give 2.25, which should counteract the effect of this concentrated load. Now, you see, the condition for this loading is basically the same everywhere. So we need to take just one section anywhere and then find our equations of shear and moment. So if we assume that we take a section, for example, anywhere, for instance, take a section here. Let's just take another color, maybe green. If you take your section here at this point, right? So now this distance up to this point, this is x. We used to call it x. Now this height, if you need to know this height, so as we said, we have these two triangles, the large one and the small one. They are actually equivalent somehow. So if we take, for example, call this O, this height O, this is the height we need to find. So if you say 1.5 over the distance for the large triangle equals that thing that we need to find, which is the value of the distributed loading for this small triangle, O over the distance. The distance is x. So you get this value of distributed load, the height of this distributed load, O should be 0.5 x. Yeah, it's because it's a function of distance. Anyways, here x is unknown, kilonewtons per meter. Okay, so now we go and work with our part of this beam. But remember, later we have to convert this distributed loading, right? This part we're working with. We need to convert this distributed loading into another single concentrated load because we need to find our equations of moment and shear and so on. So basically, let's just draw another one. So if that was our beam, this section that we're working with, and we have our distributed loading. This value was, as we said, 0.5x, right? The height is 0.5x. Then this distance, we know this distance is x. Then the value of the concentrated load here must be, so let's say FR for this small triangle now equals half x multiplied by the height 0.5x. So this is simply 1 over 4. I think this is, yes, so this is 1 over 2, this is 1 over 2, so this is 1 over 4. So 1, okay, but there's another x here, so sorry, half the base multiplied by the height is 0.5x, so this is 1 over 4 or 0.25 x square kilonewtons. So this is the value. This is the value of the concentrated load for this triangle. So now it should be here, anyways. It should be here. This is the value of the concentrated load. We said this is 0.25 x squared. And now, if that distance was x, then this distance up to here is 2x over 3, right? 2x over 3. And this distance here should be then 1 over 3 or 1/3 x. Okay, so we found everything. Now, just because the beam now is not really clear to see or work with, then we have our concentrated load here, 0.25 x squared, and then we know this distance here. This is 1 over 3 x. We know we have shear and we have moment in this direction. So shear and moment, as well as we have our AY here. AY had the value of 0.75 kilonewtons. And the length of this beam, we took this length as x, right? So this is x. Now, we write down our equations. Summation of forces in the y and moment around this point is 0. So we start, this direction is positive, summation of forces in the y direction is 0. So we have 0.75, right? 0.75 going upwards, minus this value, minus 0.25 for the point loading, x squared, minus v is 0. Okay, so equation for shear now would be 0.75 minus 0.25 x squared. And remember always to write down your units. Units everywhere, in every course, whatever you take, you should always write down your units, kilonewtons. Now that's it. This is equation number 1. And now equation number 2, to do that, we need the moment, right? So take moment in this direction, positive, sorry. So we say that our m is equals to 0. So we say our moment, this one, this is positive, and then we have plus this one because it's going counterclockwise. It's plus 0.25 x squared multiplied by the distance. It's just multiplied by 1/3 x, right? So this is going counterclockwise, so it's positive. The value of the load, 0.25 x squared multiplied by 1/3. Now minus the third one, minus 0.75 multiplied by the distance, the whole distance x. It's going clockwise, so it's negative. This is 0. This should give us our second equation, which is moment equation is function of x as the following: 0.75x minus 1/12 x cubed. This is 2. So now we had our equations. We're done basically. What you need to do is just draw these equations as function of x. And we know for a fact, because as we said, the conditions for the loading is basically the same everywhere. We have only one distributed load over the length of the beam. Then these two equations are valid for x values between larger than 0 and or between 0 and 3 meters. So we go ahead and draw our beam. I'm just gonna drag it. I'm dragging this image down, sorry, just to work with that. So first you draw your shear diagram. So this is the length, and this is whatever it is. Sorry, I'm really bad at just being tidy. So this is shear in kilonewtons, and then here we have x in meters. Now you start basically substituting your values and these two equations. Now you say at x equals 0, you'll have a value of v equals 0.75. So this is the length of the beam. Let's just draw it like 1, 2, 3, and 1, 2, 3. Okay, 1, 2, 3 meters. So at 0 you have, let's say this is, I don't know, this is 1, for example. So at 0 you have 0.75 here. So this point, I'll just draw it in red. This point. Now at x equals 1, you get v 0.5. So at 1 you get 0.5. Now you actually need to see, so it's parabolic anyways, because it's a second degree equation. We need to see where, we need to find where it intersects the x-axis, like the 0 or the point on the beam, or the length, or the x value that would give us a value of 0 shear. So here you just equate your equation to 0. You say that 0.75 minus, this is your equation of shear, 2.5 x squared equals 0. So here if you solve for x, it will give you a value of 1.73 meters. So that was 1, this is 2, this should be somewhere here probably. So this is 1.73. So at 1.73 you'll have we'll have 0 value for shear. So now probably it goes something, it's not linear, please just note it's not linear. Now go take other values. For example, we said 0, 1, take it at x equals 2. So v in this situation is 0. Minus 0.25. It should be minus because now it's going in the minus direction. So this point is minus, so probably here. So yeah, this point probably. Okay, so now at x equals 3, the last point, we find a value of v, you'll get a value of v of minus 1.5. Definitely all of these values are in kilonewtons, be careful guys. So here, so if that was, well, I don't know, somewhere here, so probably here, I don't know. So your curve will look like something like this. Again, this is not linear. This should be curvy somehow. Huh? So this is your shear diagram. You might use Excel or Minitab to get better drawings. Anyways, this is just probably you get the idea. Anyways, now we're done with this one. Now we have to work with the moment equation. We need to draw the bending moment diagram in the same manner. Now, remember from the previous video, we said that at this value, where we have 0 value of shear, at this point exactly, we'll have maximum moment. We'll have maximum moment. So we go into our moment equation. We plug this x value, which is 1.73. This was 1. Yeah, this is 1.73. We plug this value into this equation to find the maximum moment. So let's just draw our equation, our curve first. This is the same distances, 1, 2, and 3. And this is x in meters. This one is our bending moment in kilonewtons per meter. Okay. Now, the maximum value would be at this distance, 1.73. So, in this equation, you find the moment there. So, maximum moment would be at x equals 1.73. So, this is 0.75 multiplied by 1.73 minus 1 over 12 multiplied by x cubed, 1.73 cubed. Here you'll get a value of, I think, 0.866, 0.866 kilonewtons. Sorry, this is not kilonewtons per meter. This is, I'm sorry, I apologize. This is just kilonewtons. This is kilonewtons meters, not per meters. Kilonewtons meters. I apologize. That was distributed loading. This is moment. So this is kilonewton meters. So 0.866, if we assume, for example, this is 1, for example, so probably 0.8 something would be here. This is the maximum value at this point. So here, this is the maximum value. Okay, what about, now let's try to plug other values. At 0, at x equals 0, you'll get m of 0. So at 0, you have 0. What about 1? So at 1, x equals 1. So now m would be 0.66 or 0.66, yes. So we go here at 1. I don't know, 0.66, probably somewhere. I don't know, here probably. So, yeah. Okay. So this is 1, this is 2, this is 3. Okay, so it would be something like, okay, so this is the maximum point. It's also curvy as well, sorry. And then let's just find that moment at x equals 2. Calculate for that. You'll find m of 0.833. So now it started decreasing a little bit, so probably here. Yeah, probably. I'm not really good at drawing, so probably here. It's just going down. And then at 3, what do you expect the value at 3 would be? Maybe some of you already guessed, so that would be exactly 0. So try it yourselves, you see it's 0. So then the peak is skewed to the right, a little bit to the right. It's not really symmetrical. Please try to draw it using your whatever softwares you have. You would get something like skewed. This curve or this half or this portion will be skewed to the right. Anyways, that's it, guys. I mean, you can try to draw these things using Excel or Minitab to have better drawings. This is the main idea. Just basically see where you need to make your sectioning or your section, and then apply your equations of equilibrium to get or to see how these or how the shear forces and moment actually change across the length of the beam. That's it for today. Thank you very much. We will continue later.